Welcome to Module 4. We are going to discuss probability now. And this is going to be a little bit of a detour from what we've been doing. However, I think it'll be a pleasant detour for most of you because a lot of this material that we'll talk about will be a review of various things that you've seen in high school. Although we will cover some new stuff also. So what exactly are we going to do? Well, 4 things to be specific. First, we want to understand why is there a need to introduce probability theory in statistics and what does it do for us? Then we want to lay down some basic conceptual pictures of how we think about things using probability theory, and then talk about some definitions and notations that we're going to use throughout the rest of this class. Then we're going to take a slightly different track. Probability theory itself is a branch of mathematics. It's not part of statistics. And so we're going to begin to look at probability theory in a purely mathematical way and introduce some formal rules that we're going to use to compute probabilities. But then we want to come full circle back to how we are actually going to apply these results in statistics. Okay, so let's get started. Now, in this first video, I'm going to only talk about the first 2 points, just the basics. The next video, we'll go into the actual mathematical rules for how we use probability theory. And then finally, in the last video, we'll talk about how we're going to use these results later on in the class. Okay, so why do we need probability theory? Well, we said before that statistics is a rational process or a science for making decisions using data. And what that means is there's a rational basis. There's a reason why statistics works. And it turns out that that reason is probability theory. And so probability theory is going to give us a bunch of mathematical facts that we need to understand data and be able to work with it and do computations. How does this work? The key thing to understand about statistics is that statistics is a study of variation. If we had no variation in our population, so if we picked some variable, say height, and everyone in the population had the same height, there was no variation in the value of the variable, or there was variation, but there was no variation in the likelihood that we could get a certain value. In other words, the likelihood someone's going to be 4'8" is the same as the likelihood someone's going to be 6 feet. If either one of those situations occurred, we wouldn't have statistics. And the key to understanding variation is that it's not chaotic. The variation forms patterns, and this is really important. So these patterns are used to describe data from a lot of different sources. They're very versatile and very useful. One pattern, for example, that we're going to talk about a great deal in this class is the bell-shaped curve. We're going to call it by its statistical name, the normal distribution. And we're going to see that this pattern describes a lot of different types of data. So for example, if we're looking at the results of standardized test scores, IQ, SAT, ACT, they tend to have this nice bell-shaped curve. And notice what we mean by pattern. In the last module, we talked about how we were trying to fit this chunky histogram from the sample data to this nice smooth curve. And we said that's what we think the values in the population actually look like. That's that pattern we're looking for. If we look at physiological measurements like blood pressure, height, things of that nature, again, we see the data fits this nice bell-shaped curve. One application that we're going to use a lot, since this is a course in business statistics, are deviations from manufacturers' claims. As an example, you come home tonight, you go to open up, say, a box of Raisin Brans. If you look at the box, it'll say that the contents weigh 16 ounces. But if you actually take that specific box, empty the contents out, and weigh it exactly, the likelihood it's going to be 16 ounces is very, very low. And so the variations of the weights of those Raisin Bran boxes from the manufacturer's claim takes on this bell-shaped curve too. And it's amazing that data from all these different diverse sources that have nothing in common with each other all have the same pattern. Now, probability theory leverages that because what it does is it's able to find a mathematical formula that can describe all of these patterns. The nice thing is that even though we're going to work with these formulas, we're not going to have to memorize them, and we're not going to have to actually compute anything by hand. They're all embedded in StatCrunch. But we are going to use the formulas that StatCrunch is going to store for us to compute outcomes, make predictions, look at expected values, and all sorts of things. But before we can do that, we have to really understand some basics about how we think about probability. So whenever we're talking about probability, the most primitive notion we have is of what we call a random experiment or a trial. And essentially, this is something that satisfies three criteria. The first is that it's anything that can happen. Well, that's very general. But we have to know all the possible outcomes that could occur in a single experiment in advance. However, if we're actually considering a specific experiment, we cannot know its outcome before we perform the experiment. Now, this sounds very kind of abstract, so let's work with a concrete example. Let's consider the experiment where I roll a die, and I record the number on the face of the die that's up. And so I can look at the sample space, which is the term we give to all the possible outcomes for one experiment. And so in the case of the die, it's just the numbers 1, 2, 3, 4, 5, 6. So rolling a die is anything that can happen, and I know all the possible outcomes that could happen before I roll the die. However, I can't know what's going to happen on a specific die roll until it's performed. And if you ever figure out that last one, we'll go to Las Vegas and make a lot of money before the casinos bar us. Now, this is a very conceptual picture. We want to make it more precise so we can begin to do mathematics. So we're going to introduce a few more terms here. First, we're going to talk about a simple event. And that's any outcome that can occur from one experiment. So again, going back to our die roll, the outcome that I roll a 3 is an example of a simple event. Generally, however, we're interested in more complicated things than simple events. So we introduce a more generic term, which is an event. And while I could give you a very precise and sophisticated mathematical definition, one of my statistics teachers, I think, said it best. He said, an event is anything you can bet on. And I think that's really the way to think about events in a practical manner. If you look at probability theory, for example, it originated from betting. Mathematicians were trying to figure out the odds for various games of chance, like rolling a die. And even today, if you look at the major advances in probability theory, a lot of them are used for financial instruments, like stock market, financial markets, things of that nature. Just a more civilized and legal form of betting. So going back to our die roll example, I could say the event could be that I roll an even number. I could go to Las Vegas and I could bet on that. Now, before we get into the weeds, let's go ahead and introduce a few more general terms that's going to help us here. One's called a sample space, which we already talked about, and the notation we're going to use is capital S. For events, we're going to use capital letters that tend to be more towards the beginning of the alphabet. And finally, probabilities. When we want to talk about the probability of an event, we're going to use capital P to stand for probability, and then we're going to put parentheses and inside the event that we want the probability of. And so just to make sure that all of this is kind of concrete and we understand this Well, let's look at a few examples. The first is our die rolling example. So we could let our sample space, capital S, be equal to the set 1, 2, 3, 4, 5, and 6. Very often we represent sample spaces as sets. The event that we roll an even number would be the event capital E, and it's equal to the event that I get an outcome in the set 2, 4, and 6. And finally, if I wanted to look at the probability of this event E that I just defined, I would write P and put in parentheses, and inside put the event E that I'm interested in. And of course, if we were rolling a fair die, that probability would be 1/2. So let's just practice really quickly to make sure that we have this down. If we look at the random experiment that a hurricane occurs and we measure its category, maybe say at a specific time and location, the outcomes that we could get would be 1, 2, 3, 4, and 5. Those are all the different categories a hurricane can have. And we could look at an event. So the weathermen, for example, might talk about the probability that we're going to have a category 3 or higher. We could look at a more common example like flipping a coin, and we could record the sequence of the faces that were up. And we'd have 4 outcomes in our sample space. Heads, 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 then tails occurred, tails, then heads, and tails, then tails. And I could define an event, say that I get at least 1 heads. So this would be the probability that one of the first 3 outcomes occurred. And we know again that for a fair die, that would be 3/4. Finally, we could talk about a different experiment, a slight variation, where again, we flip a coin 2 times, but here we don't record the sequence of the faces that came up, but we simply record the number of times that heads occurred. And so the possible outcomes would be 0, 1, 2. Right? If I rolled a tails, tails, that would be 0 heads. If I rolled these middle 2 outcomes, heads, tails, or tails, heads, that would be 1. And if I rolled heads, heads, that would be 2. And again, I could do the same thing. I could look at the event that I get at least 1 heads, which would be the event that I get 1 or 2. All right. The interesting thing about these last 2 examples is it illustrates how important it is to define your random experiment well. Notice that the random experiment is not just what happens, it's also what you record. So in these last 2 examples, the same thing is happening. I'm rolling a die once. However, what I'm recording is different. In the second case here, I'm recording the sequence of faces that turned up. Whereas in this third example, I'm simply recording the number of heads. And so it's important to be aware of that. Okay, what is a probability? I'm not going to test you on this. This is not going to be on the homework, the information on this slide. However, I think it's important to realize that probability actually is well defined. And there are a lot of different interpretations of probability. So we tend to think of probabilities that we know as being really kind of cut and dry. But it turns out there's at least 3 different interpretations of probability. We're going to talk about one called the Kolmogorov axioms, developed by a mathematician from Russia whose last name was Kolmogorov. But there's also an interpretation from Cox and Di Finetti and a number of other minor individuals that people sometimes like to use to think about problems in certain circumstances. Okay, so to start off with, a probability is essentially a function, and it's going to map events to real numbers. It has to satisfy 3 conditions for our interpretation that we're going to use here. The first is that the probability of any event has to be non-negative. So for example, going back to our die rolling example, the probability that I get an even number on a single roll of a die can't be minus 1/2. Secondly, the probability that something occurs in the sample space always has to be 1. Okay. So notice what this means when I'm writing the probability of an event. What it really means is the probability that an outcome in the event occurs. So the probability that the outcome in the sample space occurs is 1, because the sample space is all the things that can occur. And finally, and we're going to talk about this third condition more, if I have two events that have nothing in common, no outcomes in common, if you go back to the die rolling example we've talked about, the simple event that I roll a 3 and the event that I roll an even number have nothing in common. There's no outcomes that are in both events. So in that case, the probability that one event occurs or the other event occurs is the sum of their probabilities. And finally, I want to talk about the different types of probabilities, and this is something that you will be tested on. It turns out there's 3 different types of probabilities. In other words, there are 3 ways of computing probabilities that are all consistent with that definition that I gave on the previous slide. The first is one you're very familiar with. It's called a theoretical or a formal probability. And these are exact probabilities we can compute using math. And we're going to actually compute some of these probabilities later on. And usually these things happen when we have simple events that are all equally likely to occur. And so not surprisingly, these sorts of probabilities occur a great deal in games of chance. So the sort of games that you play in Las Vegas, people can use mathematics to compute probabilities, and they do. And that's the reason why card counters are strongly discouraged from going to Las Vegas, because they will not be allowed to patronize those establishments for very long. Okay, we're going to talk next about what we call empirical probabilities. And this is the way we compute most probabilities in the real world. We use data and we compute a relative frequency to estimate the actual probability. Suppose, for example, I want to know what is the probability a person's going to get cancer. There's no formula for this. This is not a theoretical probability. How do we come up with this? Well, we estimate it from data. Okay, and the data is going to give us a relative frequency, which we talked about before. I'm going to take the number of people in my population that had cancer and divide it by the total number of people in the population. And that's an estimate that a randomly chosen person will get cancer. Now, why does this work? This is based upon a mathematical fact called the law of large numbers. And the law of large numbers says that as the population size or the number of trials becomes arbitrarily large, it goes to infinity, this relative frequency begins to stabilize and converge to a single value. And so just to illustrate this, okay, if you flip a coin, these are the number of coin flips. And this is the percentage of the flips that came up heads. And so you can see that what's happening as the number of flips gets very, 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 very large, okay, the probability of heads, the percentage of times that I obtained heads begins to converge to 1/2. So this is a really important fact. People abuse the law of large numbers. Okay, sometimes they think what it means, and it doesn't mean this, by the way, is that, for example, if I'm flipping a coin a whole lot of times and it keeps coming up heads, I'm due tails. That's totally false. If I flip a coin and I get 3 heads in a row, and the coin's a fair coin, the probability I'm going to get tails is still 1/2. It's no more likely to occur. So you see this a lot like in sports, right? A baseball player will get up and he struck out 3 times. And the announcer will say, oh, he's due, the law of averages says he's going to get a hit. No, it doesn't. All right. It says something totally different. So people kind of misinterpret this fact. The last one is one that you hear a lot, and this is what we call subjective. And this is where a person's basically making a guess. So, for example, there are a lot of situations where we cannot compute from data and we can't compute from a formula, and yet people can make estimates. For example, what's the probability that Angelina Jolie will go out on a date with me? Well, we can estimate that. It's going to be 0.000000001. Very, very small, even though we don't have any data on that, and there's no formula. Now, sometimes people think that subjective probabilities are not very useful, and sometimes they're considered really low quality. And there's 2 things you have to understand. First of all, it depends on the source. So if a person's an expert opinion, and they're an expert and they're giving you their expert opinion, then the subjective probability actually has some weight, okay? And the reality is that most probabilities we compute in real life are actually a gamish of these two different probabilities, empirical and subjective. It turns out that when insurance company is computing the probability that they're going to have to pay out a claim, they use data, but they have to weight the different types of data different ways. So how should they weight credit score versus past driving history versus number of tickets that you've obtained, right? Well, those weights are subjective. And they kind of have a way of balancing them out, but nevertheless, they are subjective. Okay, so that's all for basics of probability. And in the next section, we're going to go on and we're going to start to talk about probability rules.